All right, so we come to this question in problem 7.2, and this is question 13. 7.2, question 13. Okay, now we have this question we need to formulate our linear programming on and to also solve it. But the first thing is for us to formulate the linear programming. So formulate the linear programming. So the first thing, one, is to formulate the linear programming problem. Okay, we want to formulate the linear programming problem. Okay, so let's read the question and see how to formulate the linear programming problem. A plant wants to minimize its daily cost without affecting the daily production of product A and B. It must use information concerning its production given in the table. So we have product A, the cost for workers, the cost for raw material and inventory, and then the same thing for B. For example, each unit of A requires 50 to be spent on workers and 60 to be spent on workers for B. The available money per day is as follows: $800 to spend on workers, that is the available money. You cannot spend more than that. And then we have $1,500 for raw material, and for inventory is $300. If the plant has a daily budget of $3,000 for product A and $5,000 for product B, how many of each product should be made per day to minimize the cost? So we are doing minimization. What is the daily minimum cost? Okay, so the first thing we are going to do here is to formulate the linear programming problem. Okay, if you look at the linear programming problem given, like the one that is given in this table, okay, so we are dealing with product A, we are dealing with product B. For each product, for product A, we have the number of workers and then the money spent on the workers, money spent on raw material, money spent on inventory. Okay, so for B also we have the same thing. Okay, so we can see that if we can let our product A to be X. We are going to still write it out, but let's just try to get something out first. So we can let product B to be Y. Now, if you read at the question, we are supposed to have like a limitation on any of these or on all of these. So let's read it to know the limitation. $800 to spend on workers. So the number of the money to spend on worker is 800. That shows here we have 800. And because that is the total available to spend on workers, it cannot be greater than 800. So it cannot only be less or equal to 800. So that is very important to know which of the inequality to put. So now for workers is less or equals to 800. Now for raw material also the same, because that is available. So less or equals to 1,500. This one also is less or equal to 300. Okay, that is fine. As soon as you are able to get this, you are good to go. Then let's read again. In this question, we have this $300 for product A and $500. That is, the plant has a daily budget. And this daily budget do not have a limitation like we have here. Okay, so that gives us the objective function. That will be our objective function. So we will have minimize. There we will have minimize. There we will have minimize. So before that minimize, there's also need to define our variable. Please, that is very important. when you are dealing with linear programming, when you are formulating, to tell us what is your x, to tell us what is your y. Okay, don't just write x and y without telling us what it is. So let the number of product A be x, y that of product, the number of product B be y. Okay, so how many of each product should be made? Okay, yeah, so that is the number. So now, because product A is x, product B is y, so we can now have for workers, but objective function first. So now our objective function, is minimize 3,000 for A and 5,000 for B. So that means it will be 3,000x plus 5,000 y. Okay, that's the objective function. I can call it z. So I can say z equals to that one. That is our objective function. And I'm minimizing it. I am minimizing it. Okay, so let's now go to our constraint. Subject to, the first one is the workers. Okay, the cost on the workers. So that is 50x, 60y, then less or equals to 800. Okay, so we have 50x plus 60y less or equals to 800. Okay, the second one is 100x 250y less or equals to 1,500. 100x plus 250y less or equals to 1,500. And then the last one, which is 9x 7y less or equals to that. 9x plus 7y less or equals to 300. Okay, we don't have another one there, but don't forget this is a real world problem. In real world problem, we must have our non-negative constraint. That means x is greater or equals to 0, y is greater or equals to 0. These two can be combined sometimes to write x, y greater or equals to 0. Sometimes we write it like this, and then sometimes we can write it separate like this. Okay, all right, so this is our linear programming formulation of this problem. Linear programming formulation of this problem. So what we need to do now is to solve this by the method of, with our graphical method, to draw the graph of the constraint. We are only drawing the graph of the constraint, and after drawing the graph of the constraint, we look for the visible region. And then the corner point of the visible region. And then we pick the corner point and put it into this objective function to look for the minimum point, the minimum cost. So that is the, because we are asked to maximize, so we are looking for the minimum point, and that will be the minimum cost that we are asked to look for. That will be the minimum cost. Okay, so at the minimum cost, the point of x and the point of y will be each of the product that's supposed to have. Don't forget x mean product A and y mean product B. So at the minimum cost, the point x, y will be the point of each of the product that we are looking for. Okay, please ensure that you understand.